setting are the real scalars. Okay, so if you wish, okay, you may go to the topic 2. Okay, I believe topic 1 and topic 2, we cover the idea and the definition of the linear independency, right? So by using those techniques, okay, so we are going to set up the relationship like this. Okay, so for each vector in the set, okay, I try to embed a real scalar, okay, together with the vector. So alpha, beta, gamma here will take real number, okay, or you can simply consider they will take real values. Okay, so these 3 vectors are given by the question. Okay, so under the multiplication of this scalar and the vector, okay, we sum them up and then I try to make it to be a 0 vector. So you can see on the right hand side, it is a 0 vector. All right. So this is the definition of this is the starting point, okay, to check for the linear independency. Okay, so when you take a look at the left-hand side of the relationship, we can further simplify it, try to incorporate, okay, the 3 respective vectors, okay, back to the one vector, okay. Of course, the element will be in a bigger size, okay, in longer size, okay, a little bit complicated. Okay, so our job, okay, in this question, okay, we may ask ourselves, okay, what is our job? What is our target? And what we are going to solve for? Okay, actually, if we want to solve for, or if we want to check the linear independency, we are asked to find out the value of alpha, beta, and gamma, right? And our ultimate objective is to check whether or not alpha, beta, and gamma to be 0 at the same time, right? So if that is the case, that means we will be able to claim the relationship is linearly independent. Am I correct? Okay, so if you agree, okay, so we are moving on to this target. Okay, so let's take a look. We are going to solve for the following system. I just compare, okay, the entry on both sides correspondingly. Okay, for example, the first guy, beta plus 2 gamma, actually corresponds to this, for the first entry, 0. So you can see this is the one. I just use the blue arrow to connect. All right. So secondly, okay, the second guy, I try to connect with the second element on both sides. Okay. So that's why you can see alpha plus beta equals 0. Okay, not to mention the last guy. Okay, we are going to compare the both sides for the third element. All right. So okay, I do something similar. Okay, so you can see, okay, that's why we have this system, okay, 3 linear equation, okay, because alpha, beta, and gamma are what we want to solve for, right? Okay, so you simply treat it as a variable in this case, okay? So, of course, at this moment, you may want to use whatever you learned previously in topic 3, right? For example, you may want to write down the Gaussian elimination, right? Gaussian-Jordan elimination, or the inverse formula, and then, or if it is if there is a unique solution, okay, so Cramer's rule and so on and so forth, right? Okay, so basically, okay, of course, you can do whatever you want, and as long as the method, the concept, and even the conclusion is right, okay, you are totally fine. You are totally welcome to use whatever method you feel comfortable, okay, or you feel confident, okay. And also now, I would also like to give you another angle to tackle this problem. I would like to do it by inspection, okay, by inspection. Okay, so I hope you can see something new here. Okay, so by inspection, okay, I would like to check the first and the third equation, okay, the first and the third equation. From the first one, you can see that beta plus 2 gamma equals 0. If we can substitute, okay, the result, okay, back to the equation 3, okay, so you can see that the underlying one will become 0. Indirectly, you should be able to tell alpha to be 0, right? Right? Okay. So of course, I write down the idea. Okay, so-called by inspection. So you can see that by inspection we can make use of the first and the third equations. My handwriting is not clear. Hey, what happened? Okay, here. Okay. Oh. Okay, interesting. So alpha. Okay, let me repeat. A good time to repeat what what I did. I just talk about. So alpha equals 0 by inspection, right? So by inspection, we can make use of the relationship of the first and the third equations, and we can claim that alpha to be 0. All right, this is the first observation. How about the second one? If we can know alpha to be 0, can I make use of the second equation and make some conclusion for the beta, for the value of the beta? Any idea? Very good, very good. Because you see that if alpha equals 0, so 0 plus beta equals 0. So we have only one choice, beta to be 0 in this case, right? Okay, again, we are going to do it by inspection again, right? But we focus on the second equation. Okay, we focus on the second equation. Okay, maybe I'll give one more reminder. Since alpha equals 0, right? Okay, of course, I just briefly write down some keywords. Okay, this is not a complete sentence, or this is not a correct pattern, right? Okay, grammatically correct. Just for your quick reference. Okay, how about gamma? How about gamma? You can see that actually I can borrow, okay, the first equation or the third equation again, because only these two equations involving in gamma, right? Okay, so if alpha or beta, okay, for the first equation, if beta is 0, so naturally, okay, you should be able to know that gamma to be 0 again, right? Okay, again by inspection. Okay, or you can argue that, okay, I want to use the third one. Why not? Okay, let's do it. Okay, if alpha and beta to be 0 at the same time, so the same conclusion is here, right? Okay, so you can know that alpha equal beta equals 0. Okay, so you will be able to use the first and the third one. I mean the first equation or third equation to make the following conclusion. Okay, so I just want to give you another angle, okay, to view the same problem. Of course, you can use the standard technique, Gaussian elimination, and blah, blah, blah. Okay, I just mentioned, right? Okay, so I hope you can gain something new here. Okay, go back to the original question. We are targeted to, okay, we are targeting to achieve the result for linear independency. And the target, okay, is to show that alpha, beta, and gamma, all of them equal to 0 at the same time, right? Okay, so that's great. Okay, this is what we want. Okay, so now, from this result, okay, so we can claim that the set capital S is the one, okay, used at the very beginning, okay? Nothing new, okay? I just want to tell you, just want to conclude that the set capital S is linearly independent. All right, so this is the first result. So far so good. This is not the end of the story for this example. And I would like to consider another thing which is very essential in order to claim for the basis. All right, so let's move to the next page, 16. The second procedure, we will need to verify whether or not every vector, okay, every vector in the R3 space can be expressed as a linear combination of the vectors, okay, shown in S. Okay, there are 3 vectors, right? Okay, you can check the previous page. I would like to show and verify every vectors in R3 space can be expressed as a linear combination. All right, as a linear combination of the three vectors shown in or contained in capital S. Okay, the second objective. All right. Okay, so let's see how we are going to tackle this problem of this part. So suppose there is a arbitrary vector in R3 space. Arbitrary vector means that I randomly pick one, in general, without loss of generality. I simply assume, there is a vector XYCs. XYCs can represent any points in the R3 space, to make sure, the generality, So now I would like to figure out, the following relationship, in terms of linear combination. In other words, I would like to see, or I would like to check whether or not I can rewrite the vector XYCs in terms of the three vectors, These three vectors on the right-hand side of the equation, the three vectors are mentioned in the initial setting of the capital S, right? Okay, and again, we also associate some constant term. Lambda. Oh, sorry, I blocked something, right? I associate a lambda, mu, and sigma. Together with the vectors in S. In order to form so-called linear combination. Again, I hope you can still remember we discussed the idea of linear combination in topic 2 and in the very beginning of this material. Am I correct? So I hope this is not new to you. And then our job, is to find out whether or not this kind of real constant lambda, mu, and sigma exists or not. If yes, if they exist, or if we can find out them, we can claim that the arbitrary vector XYCs can be represented as a linear combination of all of the vectors, all of the three vectors in capital S. This is our target. All right. So in other words, our job is to solve for, I put it down. Our job to solve for lambda, mu, and gamma. All right. This is our job, and this is our target. So I would like to take the similar approach as the procedure 1. I would like to equate on both sides, all right, and try to compare them. I'll try to find them out, one by one. So that's why, I can form another system of equation as follows. 3 equations because we have 3 elements for the R3 space. So guys, I would like you guys to take some times, to solve for me, to solve for the lambda, mu, and gamma. Not gamma, sigma. To solve for the 3 constant term. I hope it will not take you so much time. So time now is 4:46. How about we do it in about 6 minutes, and then we check the suggested answer around 4:50. So this is your turn. I hope you can find out have some finding, for the lambda, mu, and sigma. Do you need more time? Interesting, right? Is it interesting? Okay, so even though you may not work with some real number, okay, or some numerical value, okay, but I believe you guys should be able to do it successfully and easily. Very good. Okay, I see quite a number of you get it done. Okay, and get it successfully done. Okay, so let's take a look to suggest the answer. Of course, some intermediate step I don't show you. Okay, you may treat it as a practice. Okay, so for lambda, okay, which is half times 2x minus y minus c, okay, and then mu y minus x plus c's value. Okay, the last guy, sigma x minus c's. So maybe it is worthwhile to take some time to analyze it a bit. Okay, so can you tell me, because x, y, c's are arbitrary vector, right, in the R3 space. So in other words, x, y, c's is going to take any real numbers, right? Okay, so you can see that for lambda, okay, you can see a group of real number add together, subtracted from each other, right? Okay, and times another real number, 1/2. Okay, so you should know that this is belong to real number. Secondly, or similarly, okay, all of them should be real number. Okay, all of them are real number. Okay, because the interaction among real numbers, of course, they will return us with real numbers. Okay, so basically, okay, we are done. Okay, for this part, because our target, okay, is to solve for lambda, mu, and even the sigma, right? So now we basically get it done, and then we have, I use another color, okay, x, y, c's, okay, actually equals half time 2x minus y minus c's. Okay, the first vector, which is 202, right? Secondly, I should have enough space, okay? Okay, y minus x plus c's times another vector, 1, 1, 1. Last but not least, okay, x minus c's times the last vector, 0, 1, -1. Okay, so in other words, okay, for a arbitrary or for a random vector x, y, c's, okay, in the R3 space, I can successfully express the vector x, y, c's in terms of the three vectors in capital S, the set we mentioned or we are provided in the very beginning, right? Okay, so that in other words, they are in a linear combination of those vectors. Agree? So we will be able to draw the overall conclusion, okay, for this example. Okay, but before that, okay, of course, some further description. Okay, we made it verbally, okay, because x, y, c is a random vector, I take real number, and so on and so forth. Okay, I just want to tell you another idea only, okay, verbally. Okay, so now this is not the end of the story, okay, because we need to make the final conclusion for this example 5. Okay, so combining these two results. Okay, combining the results of these two parts. Okay, we can conclude that the set capital S, okay, is a basis, okay, for R3 space. All right. So far so good. Okay. Don't worry. Okay, I know this example may be a little bit lengthy. Okay, I will show all of the page as usual. Okay. So I hope you can gain the idea first. Okay, and we can do the other job later. Okay, so far so good. So basically, okay, we are done for the idea of basis. Okay, by using an example, okay, to show the procedures we need to go through in order to verify the basis. Okay, If this is okay, so we will move to the next subsection. Okay. But before that, of course, there is a practice question consists of 3 subparts. Try it. Okay. I believe you guys should have no problem for this question, to enhance your understanding. Okay, and let's move to the page 18. Okay, new concept again. Okay, dimension. All right. So actually, dimension may not be new to you again. In other place, in other course, or even based on your understanding, okay, you already talk about this or you are already learn about this. For example, when we are going to talk about real numbers, actually it refers to one so-called one-dimensional space. How about this guy? R2 space, okay? R2 space. Sometimes we call it two-dimensional space, XY plane, right? Okay, not to mention, okay, R3 space, XYZ plane, XYZ's coordinate, we call it three-dimensional. So when it comes to dimension or dimensional space, okay, actually this is not a new concept to all of us. So I would like to give you several ideas, okay, in this section, okay, and then try to connect with what we have learned, okay, before. So in the last part, okay, all of the bases for the R2 space will contain 2 vectors, okay. You may go back to the last section, okay, to check with it. Okay, and then for the basis, okay, of the R3 space, it has 3 vectors. Okay, so interestingly, okay, the value of the dimension, okay, R2 or R3, okay, I will simply call it the value of the dimension, okay, will be the same as the number of vectors inside the basis. Okay, is it a coincidence or it happened by chance or it will always happen? Let me tell you the fact. Actually, for every basis, okay, for every basis of R2 space, it will consist of 2 vectors exactly. Okay, for R2 space, it will consist of 2 vectors inside the basis exactly. For the R3 space, okay, the set, okay, the basis, okay, will contain exactly 3 vectors. So in general, okay, if you have an n-dimensional space, naturally you will have, the basis for this Rn space or n-dimensional space will have exactly n vectors to form, okay, the basis. Okay, so I simply write down or write down the connection with you. Okay, 2 vectors in basis. Okay. R3, okay, you can see that 3, okay, you see what I mean, right? Okay, because I want to write several more example. So if you are going to extend, okay, I forget to make it nice, okay, sorry for that, okay. Okay, when we extend to a general case, n-dimensional, okay, so we will have n number of vectors in the basis. All right, so this is the finding, or this is the fact, okay, I would like to tell you at this moment. All right, okay, but here, I just want to remind you something. So you can see we use several keywords, for example, basis, right, and base. Okay, so I hope you guys can make it clear. Okay, base refer to the single basis. Okay, when it comes to base, okay, it means multiple bases. Okay, so you can see I use the corresponding word. Okay, for example, all of the bases, okay, in R2 space means that more than one basis, okay, for R2 space, okay, but they will contain 2 vectors. Okay, refer to the statement. Okay, so I hope you can see the similarity or the relationship of these 2 words. Okay, don't get confused. All right. Okay, so based on what we have discussed so far, okay, I would like to lead you to the first theorem, okay, of this subsection. Okay, theorem 1, and this is very interesting and very important theorem. Okay, theorem 1. Suppose you are given a vector space V, okay, of a Rn space. Okay, so for a vector space V, okay, there is it contains a basis. Okay, it contains a basis. Okay, and then I use a capital B, okay, to denote the basis. In particular, in the set, Okay, as I mentioned, Rn space, of course, the basis will contain n vectors. Okay, so you can see in the set B1, B2, B3 until the last guy, Bn. So you can see there are n vectors. Okay, so perfectly met 2 until Bn. Okay, if we can find there is another set, also in the same vector space, capital V, but the set contain more than n vectors. All right, so and particular standard basis. Okay, for the Rn space. Okay, as usual, we use okay the old notation. Okay, capital B to denote the basis for the Rn space. Okay, so based on the description, okay, we have n vectors for the basis of a Rn space. Okay, so there are n vectors. All right, and we have a special name for this kind of basis, which is called standard basis. Okay, you can check the last section. Okay, before we start today, right? Okay, we describe. I mean, in the last class, basically, okay, in the last class, at the end, we discussed the idea about standard basis, right? Okay, we borrow, okay, the same idea here. Okay, now if we consider, okay, or we let, okay, capital S another set, okay, okay, containing some vectors, vector 1, v1, v2, blah blah blah, okay, vm. Okay, suppose there are m vectors. Okay, so we let S to be a set of m vectors. Okay, in V. That means we are talking about the same vector space. Okay, otherwise it is meaningless to compare, right? Okay, so firstly, I assume there is another set called capital S. It consists of m vectors in the set, and the set is in vector space capital V. In particular, where, okay, the value of m is greater than n. Okay, so by using the theorem 1, so we can conclude that the set capital S, the set capital S must be linearly dependent. All right. So this is the essential or the underlying meaning of theorem 1. Okay, so I would like to show you a numerical example. Okay, so I will move to page 19 and the example 6. Okay, all right, example 6. Okay, we are ready, right? Okay, so let's take a look. Now, I would like to consider R3 space, okay, to be a little bit simple. Okay, we consider three-dimensional space. So, of course, based on the description, if we form or if we know there is a basis, it must be containing 3 vectors, right? Exactly 3 vectors. Okay, so we simply stay here. Okay, so now I would like to apply theorem 1. Okay, so if there is a set consists of 4 vectors. Okay, of course, again in the same R3 space, in the same vector space, right? Okay, but the new set consists of 4 vectors. Okay, and namely 1, 1, 0, 0, 0, 1, 1, 1, 2, and 0, negative 2, 1. Theorem 1 tells us that, okay, this set must be this set must be linearly dependent. Okay, must be linear dependent. Because we can check, okay, the following. Okay, we can check the linear dependency among themselves. Okay, so let's take a look. Firstly, okay, I would also like to make use of old concepts to write down the starting relationship. Okay, for example, there is several constants C1, C2, C3, and in the next line. Okay, I don't have enough space. C4, 0, -2, and 1. Okay, I would like to see, okay, the linear combination of these 4 vectors, and I try to equate it to be a 0 vector. Of course, we are asking similar question as we did in the last several pages, right? What we are going to do is to solve for, okay, C1, C2, C3, and C4 to see what are they, okay, what are their corresponding value in order to make this equation or this relationship happen, right? Okay, and then after several algebras or after some addition, multiplication, so on and so forth, okay, we can see that actually C1 equals 1, C2 equals 2, okay, C3 equals -1, and lastly C4 equals 0. In other words, okay, we have equals, okay, a 0 vector. Okay. Okay, so of course, after some intermediate steps, okay, we lead to the following conclusion. Okay, we solve for the C1, C2, C3, and C4. Okay, and then we can rewrite the overall relationship as follows. Okay, and based on our idea, based on our concept about linear dependency, we can claim that this relationship clearly, okay, to reflect they are linearly dependent because not all of the coefficients C1 until C4 are 0 at the same time, right? So we can successfully claim that this set consists of 4 vectors, okay, must be, okay, linearly dependent. Okay, so I hope you can connect this with the firm 1, okay, in this section, okay, of dimension, right? So far, so good. Okay, seems that, okay, the time is running short. We only have 7 more minutes. Okay, so maybe I will end the teaching here, okay, and I will show you the page we covered today, okay. So let me see. Okay, we start from here, right? Okay, the term standard basis. Okay, we just use it. Okay. Okay, but anyway, okay, I just want to remind you where we discussed the idea of standard basis. Okay, so we start from this page 15. Okay. So if you if you want me to enlarge a little bit, okay, just let me know. If not, okay, I will stick to this size. Okay, and then again, for every page, about 20 seconds first. Okay, so the next page, 16. Try my best to enlarge a little bit. Okay. So at the same time, okay, I may be able to also talk about something about the midterm exam. So as mentioned, okay, we would like to have a dry run for the midterm exam, right? So we would like to practice the logistic. Okay, how to arrange the attendance taking, question paper distributing, and so on and so forth. Okay, I would like to have a dry run. Okay, otherwise we will be in trouble, right? I don't want to. How to say? I always want to minimize the disturbance to all of you guys, but it depends. Okay, so in case there's anything unexpected, okay, we try our best to minimize those issues. Okay, so we may need the so-called dry run. Okay, to get more familiar with the overall operations. Okay, until the last minute, not until the last minute. Okay. Oh, so on this page, okay, this is only a practice question. So not much particular information over there. Okay, so the next page, okay, again, it contains quite a number of information here. And now we move to the dimension, right? The section 5 of this material. And I will share with you a general policy and guideline to you very soon. Okay, we have, I mean, all of the instructors are trying to finalize the final version, okay, of the general instructions, okay, or the guideline for the midterm exam. So stay tuned for this, okay, because some of them we may need to fine tune some policy, okay, to make it smooth, okay, to ensure every one of you will be in a fair environment, okay, to sit for the same exam. And of course, we are going to do the exam, okay, by using Zoom, okay, and then we will make use of the Blackboard, okay, as the platform to, I mean, for the question distributing, and then question paper collecting. Okay, we will also rely on the Blackboard. Okay, so example 6 is the last example. Okay, we covered today. Okay, all right. So let me see. Okay, by the way, for the coverage, okay, for the coverage of the midterm exam, okay, so let me repeat. We will test, I mean, we will cover the topic 1 to topic 3 of this course. Okay, that means the topic 4 is not going to be examined, okay, in the coming midterm exam. Okay, so you can see, luckily, okay, we cover everything. We plan to cover in the exam. Okay, topic 1 to topic 3. Okay, system of linear equation, right? Okay, matrix, determinant. Okay, and so forth. Okay, some interesting stuff. Okay, or some fundamental stuff. Okay, you have to grab firmly in order to proceed. Okay, so it is good time, okay, to force you guys to study, right? Okay, to review those kind of important concepts. Okay, and then the TA today will talk about, I believe the TA will talk about the homework 1 and homework 2 in the coming tutorial, starting from 5:30 today. So you may take a rest, okay, and then focus on the description and discussion, okay, by the TA. And the TA is very nice, okay. I believe he will make the material very, very informative, okay, and very helpful for your preparation of the midterm. Okay, so okay, so I plan to do the dry run, okay, on next week, okay. Even in particular on next Monday, okay. Otherwise, it will be too late, right? Okay, on next Monday we have a 2:45 minutes class, so it should be more than enough, I hope. Okay. All right. So I think the time is running short. Okay, and then if you wish, okay, basically this is the end of today. Okay, thank you very much. Okay, and then I will see you next week. Okay. Okay, so because I have a meeting, okay, right after this class, so I will see you later. Okay, in case you have any particular question or any idea, concern, inquiry for the midterm exam, okay, feel free to send me an email. Okay, so I'm more than happy, okay, and then get back to you as soon as possible. Okay. So see you guys. Okay, and have a good day. Even have a good week. Okay, see you guys. Bye bye, guys.
Hi. Could you all hear me? If you can hear, sorry, I forgot to. Oops. Let me check. Okay. So it's time to start, and the first thing I would like to say is there are some students from the section A that they participated in the section E's tutorial, because I don't know why my VPN connections were unstable recently, so I didn't get access to the Zoom link in the morning. So I suggested them to join the Zoom link in the section E, and I will make another makeup tutorial for them. So there are another thing is maybe my connection is unstable, so there is still some possibility to get lost with the connection. So if I disconnected, so please wait for me. I will try my best to connect it back. Okay. So let's get started. I should like to record the video. Okay. Oh, I need to ask for the permission. So could you guys wait for 1 or 2 minutes? I will ask for the permission to recording. Okay. So the TA leads, okay, she replied to me. I guess she will enter in the Zoom link and help me to record. So wait for another 1 minute. I'm so sorry for that. Oh, I guess the reason that I cannot record is I didn't log into the Zoom. So I will quit and re-enter into the Zoom link. So please wait for about like 1 or 2 minutes. Hi. I will try it another time. Oh no, I still cannot record. Oh, I guess the Ying helped me to record the tutorial. Okay, so let's get started. I will start to share the screen. So can you all hear me? I just want to make sure. Okay, thank you for your response. Okay, so let's get started. Okay, welcome to the tutorial 6. In this tutorial, I will introduce like the homework review with TA, we just finished the grading of the homework 1 and homework 2. So here I would like first to share some suggestions for your assignments and also for the midterm or the final. And after that, I would like to answer some questions in our whole homework. And if you have any questions about the homework, and you can leave after, you can stay after the tutorial and ask me about the questions. I will try my best to solve your problem. So let's get started. So first, I would like to share 4 suggestions for your submission, and the first 2 are for some minor parts of the students, and the last 2 are for all of you guys. The first one is to please check the submission after you submit it. Actually, in the first assignment, there are about like 2 or 3 students. They handed in a wrong assignment, like they handed in the assignment from other courses, so that's a pity for them. And the second thing is, please be well organized for your assignments. That is, some students, they just took the pictures and they didn't shift it or rotate it, and all the words are horizontal, or so for our TA we cannot exactly say what they were writing, and we need to tilt our head to say all the words and the solutions. And for another, we get some. Yeah, okay, yeah. And for other students, like their assignments are disordered, like we cannot know, so they don't sort their answers. We need to search in the whole assignments to find where is the answer to question 1 and where is the solution to question 4. So we need to go through all the pages to find where is the according solution. So after the first 2, the third suggestion is the calculation procedures worth more than the results. I found some students, they just provide the answers, like to calculate the determinant for a matrix. They only show the results and no procedures are provided. So we don't know how could they obtain the results. And we also cannot score this kind of assignments. So I suggest that if you can, please write down more procedures as you could. That is also true for the midterm or the final. If you write down more, and we may score you some effort scores. Actually, the procedures will take about 70 or 80% of the whole scores. So please be careful to your procedures and write down as much as you can. And the final suggestion is to be careful to calculate. For the homework 2, there is 1 question to calculate the determinant. There are about 30% students, they have the wrong answers. And when I check the procedures, they may be correct, but I don't know why they made some mistake in the calculations and their results were wrong. So I suggest that you should be careful when you do the calculation. So here are some suggestions for your further assignments for midterm or the final. I hope you can follow the suggestions I propose. Okay, so let's get some feedback. No. We have finished the grading and the professors are working on combining them. So I guess tomorrow or the day after tomorrow, the professors will release the grade. Okay. Okay, so let's begin. Okay, so let's get started from the homework one. Here is the question 1.1 and the question 1.2. These two questions are examining your ability to do the matrix multiplication, and I think they are not so difficult. You just need to be careful to do the calculation. I guess they are complicated, so just do it step by step, and don't make some mistake. Why there is only the mark but cannot see what I did wrong? If you want to know what you did wrong, you can just send email to professor. Actually, we leave some comments for the grading, and we may try to add the comments in the grading parts. But for the homework one, I'm not sure about the homework too. If you have questions about your grading, you can just send a message or send an email to professor to ask for the reasons. Okay. Okay. So for the question 1.3 is to calculate the inverse of the matrix A. So how to do that? We know the property of the inverse of a matrix. That is, the matrix multiplied by the inverse is equal to the identity. So in order to get the inverse of A, we need to transform the equations we have to the form like A multiplied by some matrix, and it is equal to the identity matrix. And the matrix we write down is exactly the inverse of A. So we just try to transform the equation to that form. So here is the answers. And I guess there is one thing we need to pay attention is look, the results here. We have an identity matrix for the 3/5. So please pay attention to that. Some of the students miss the identity matrix. So pay attention to that. Okay, so let's go to the question 1.4. This question is not difficult, but it's quite complicated. You need to do the multiplication by 3 matrix. But if you follow the step, like the first matrix multiply with the second, you just use a row multiply by the column. You will get a 1 row and 3 column small matrix, and after that you use the small matrix to multiply it by the xy1, the 3 row 1 column matrix. You may get 1 by 1 matrix. So you just need to follow the steps and be careful. Yes. So that's why I suggested you guys to be careful. And it's easy to identify that. You can just write down the size of each matrices yes, because some of the students may get the results like 3 by 1 matrix. So if you check your size first, and you can just you may not make the mistake again. So let's see the question. Proof question is more difficult than calculation. Yes, I agree with that. So I will explain some proof questions like the question in homework 2. And yes, so I will explain them to you. And the question 1.5, yes, find the rank of the following matrices. Yes, you first do the row operation, and then you count the non-zero rows. So that is quite straightforward to follow the step the professors have already mentioned in the class. Yeah, so I think the questions are all straightforward. Just be careful to calculate. So the next one is 1.6. First, you write down the augmented matrix. Yes, for this one, you extract the parameters between the in front of the x value, and after that you add the last column to the end of the parameter matrix to have the augmented matrix, and after that you use the row operation to get the reduced row echelon form. So the next question is the proof question, as the student mentioned. So I will explain it to you. So suppose that we have three vectors in three-dimensional space. Suppose any pairs of them are linearly independent. So are V1, V2, and V3 always linearly independent? And if yes, prove it. Otherwise, you show some counterexample. Actually, for this question, you can just imagine, like for the V1 and V2, like if a pair of two vectors are linearly independent, that means one vectors cannot be expressed by another vector. That is like the suppose vector V1 is like 1, 1, 1, and V2 is 2, 2, 2. And V2 can be expressed by V1, so they are linearly dependent. And for linearly independent, is V2 cannot be expressed by V1, just like 2, 2, 0. And for three vectors, and you suppose that for three vectors, and each of two vectors may create a plane that can shelter those two vectors. So suppose that the third vector V3 is also on the plane. Like V1 and V2 can create a plane, and the V3 can also on this plane, because if we send a V3 is dependent on V1 or V2, so V3 may underline of V1 or V2, so we can find V3 in the V1 and the V2 space. That any pair of them are linearly independent, but actually the V3 can be expressed by V1 and V2. So that means V1, V2, V3 are not always linearly independent. And I can take an easy example. Suppose that for the three-dimensional space, x, y, z, suppose V1 and V2 are on the xy plane. Like V1 is equal to 1, 0, 0, and V2 is 0, 1, 0. And we let V3 lying on the xy space, on the xy plane. Like we treat V3 to be 1, 1, 0, right? Each pair between them are linearly independent. The V1 cannot be expressed by V2 or V3. But actually the V3 can be expressed by V1 and V2. like the V3 is equal to V1 plus V2. So here we have the conclusion that each pair of linearly independent cannot imply the joint independent. But I guess if you have the jointly independent, you can imply the pair of linearly independent. So in this question, you just need to figure out some counterexample, right? Okay, so for the next question is to consider the matrix A and find like the a to the power of p for all positive integer p. And in this question, because we don't like to have some strategy to solve this kind of a to the power of p matrix, so we just write down the p step by step. We increment the p a little by little to find out is there some recursion between them. So we just first write down the a square, and after that we write down the a cube. And surprisingly, we found that the a cube is a zero. Oh, I'm sorry for the disconnection. All right, okay, I see. Oh, okay, so could you tell me where I stopped? Okay, sure. Okay, so let's continue that. Okay, yes. Actually, for this question, we don't know some strategy to solve like a to the power of p matrix. So we just write down the a to the power like 1, 2, 3, and we try to find some like recursion between them. So first we write down the a square. First we write down the a square, and then the a cube. And we found that the AQ is actually a zero matrix. So any matrix multiplied by the zero matrix is still be a zero matrix. So we can find the recursion. So we have the solution that the a to the power of p is equal to zero matrix for all integer p is greater than or equal to 3. And for a1 or a square, you can just write down the special solution for a special matrix. Okay, so here is the end for the homework one. And do you have any questions here? So if not, I would like to continue. So then we switch to the homework 2. And for the first question, the homework, the question 2.1, I guess this question students are not performed well. So I will explain it. And for A part, find the determinant of matrix A. You can see that like the first row and the second row of A, they are similar. And if you use the row operation, and you may get a 0 row. So then you expand it on that row, you may get the determinant to be 0. So it's simple to get the determinant of A is 0. But you can also like to expand it to compute the determinant. And for the part B, to find the cofactor of C11. For C11, you observe that the cofactor of C11 is the right bottom 3 by 3 block, and is actually a triangular matrix. And the determinant A is the minus of the diagonal values, so it's -1. And then to get the determinant of matrix B, and you observe by A and B, the difference is only the left corner bottoms. The left corner elements are different. The element is different. So the determinant of B can obtain from determinant of A and subtract with the left the A11 value multiplied by the cofactor of A, and the cofactor of A is exactly the cofactor of C. So determinant of B is determinant of A minus C11, so it's 1. And the third question is find the determinant of C for any value x. You compare B and C, like the C at ax value on the first element. So the determinant of C is determinant of B plus x multiplied by the cofactor of C11. So the result is 1 minus x. And we turn to the second question. We use element row operation to convert them to the reduced echelon form. So it's also a simple question, but you need to be careful to do the calculations. The third one is also easy to find the rank. I guess most of you guys are correct in these questions, so I will skip it. And this question is, I mentioned before that many of you guys obtained a wrong result. Yes, because there are 4 sub questions. Yes, to compute the determinant, you can first follow the formula, right, to calculate it. And you can also use like row operation to transform it to a triangular form and multiply all the diagonal values. It's up to your choice, but make sure that each step is correct and won't make any mistake. Otherwise, your results are wrong. So make sure of each step. And be careful, yeah. Okay, the next question is okay, we have the 45D. Oh, I don't know the meaning of 40 or 5D. Okay, so we continue. Okay. Why we can easily say the term of A since 2 rows are equal. Because you can use the row operation, like to like row 1 equals to row 1 minus row 2, and then you just expand it on row 1. So because the values are all 0, so you choose elements on row 1 and they all be 0. No matter what the cofactors are, you may have 0. Okay, so for the question 2.5, okay. So the question 2.5 is quite similar to the previous question in the homework one to compute the inverse. And so here we aim to find the x, and we observe that the x inverse is in the equation. So we follow the same step. We want to get like the x inverse multiplied by some matrix, and it is equal to identity matrix. So the matrix we write down is exactly the x. So we just follow the step here to get the result, and pay attention to the last row. Here is still an identity matrix here. And in the part B, you just use A and B to calculate the x. And first, you should calculate the inverse of A. You can use like the row operation to get A, and you can also like use the equation, the formula. I guess like the inverse formula the professor mentioned in the class to get the inverse of A, and you just substitute all you get into the formula to get x. And in this part, many students like to wrongly switch the order of multiplication. So please be aware that you will do the the multiplication step by step. You first multiply like B by A, and then you just like for the last row of the right on the left bottom, you get the A inverse, you get B, you get A minus I identity. You just multiply from the left to the right and step by step, and don't like switch the orders. Okay, we get some questions. Okay, oh, no question. And for the question 2.6, suppose that we have a matrix n by n, and we have the symmetric property. And from the class, we know that determinant of A transpose is equal to the determinant of A, because we can expand it in row, or we can expand it in columns. So they are exactly the same. So the determinant keeps the same. And after that, because the determinant of minus A, we add the the negative label on all the elements. So when we calculate the determinant, you imagine that all the values are negative. So we will extract all the negative one outside the determinant, because we have n row and n columns. So the power of -1 is n. So we will have a factor like the -1 to the power of n behind your determinant results. So -1 to the power of n, we have n is out. So the determinant of -A is equal to the negative determinant of A. So you can use the property to get the determinant of A directly. For the next question, you prove that the A is invertible. To prove a matrix to be invertible, you just can show that its full rank, or we say all the diagonal values are non-zero. So it's quite straightforward. So you just say that you observe from the matrix, or you can do like the row operation to transform it to a reduced form, and you observe it. It's a full rank matrix, or all the diagonal values are non-zero. So you can just say that to prove it exists. And for the second part is to compute the inverse. You can use two strategies. One is to use the row operations, and another one is to use the formula directly, the inverse formula directly. But I prefer that you use the row operation, because there are many steps in your answer sheet. So we can give you some effort scores if you made some mistake to get the correct answer. And let's turn to the final question, the question 2.8. Suppose that U, V, W are linearly independent vectors. Prove that the vectors U minus V, V minus W, and W are linearly independent. I saw from the grading sheets, I guess most of you guys perform well in these questions. So I don't want to spend too much time to explain, but to show that you can use like some basic definition to help you to prove. Right? Because suppose U, V, W are linearly independent vectors. That is the same to you write down the equation like C1U, C2V plus C3W is equal to 0 because they are linearly independent. So the only solution is C1, C2, C3. They should also be 0. So you can just like follow the definition to prove that. And then for the vectors U minus V, V minus the W, and the W to be the linearly independent, you can also follow the same step. Like you write down the factors for them, like you suppose A1, A2, and A3. You can also try to solve the equations. Like you need to prove they are linearly independent. You just need to show out the factors. They can only be 0. So it's easy to prove. So you just write down the equations and you try to solve it, and you already get the solutions like to A1, A2 minus A1, and A3 minus A2. They are all zeros. And after you finish the calculation, you find that the only solution is all the factors should be 0. So that is like quite straightforward to prove that. To say other things about the proof questions, from my experience, you can just like to examine what kind of the definition you would like to use to express the conditions. Like in this question, like U, V, W are linearly independent vectors. We can use the definition of solving the equations, and all the possible solutions is they are all 0. So I think in order to do a proof question, you first need to figure out what concept we would like to examine you, and then you just use some mathematical equation or formula to write down the definition. And after that, you should express what you want to prove into the same form, and then you find like the transform from your condition to the thing you want to prove, and if you find the bridge between them, it's easy for you to prove that. Okay, so I guess it's the end. Oh, we have some question. Can I see question 2.5b again? Okay, sure, no problem. Okay, for the B part, you just like to first calculate the A inverse by what kind of method you want, and you just say the last row out on the right hand side. You need to know the A inverse B and A minus identity. You just write down all the matrix and follow the steps like from the left to the right, and don't like to switch the order. So that's a disaster. So yeah. Okay, so let me check that. No, I checked that. The inverse is correct. You can just like to multiply this result with A, and you can get an identity matrix. So I think there is no problem with the answer. Any hints for homework 3? Actually, you can send an email to me for hints, right? And in this tutorial, I only cover about the homework 1 and homework 2. Okay, yeah. So here is the end of the tutorial. If you don't have any questions, you can feel free to leave. And if you have questions, you can just stay here with me and ask the question. Oh, can I get a constant times matrix for inverse for answer? Get a constant times a matrix for inverse. Oh, you mean that if you have like an identity matrix? No. I guess the definition is because for all the questions we work on the matrix multiplication. So one constant multiplied by the matrix is not the definition of the matrix multiplication. So I guess we cannot use a constant to be the inverse. So is that solve your question? Okay, see you guys. Be adjacent myself by adjacent. Bye bye guys. By adjacent myself. Could you send an email to me because I cannot understand your question? So please give a formal description. I'm sorry for that. Okay, yeah. Okay, so we have others. Thanks and bye. Okay, cool. So see you guys. I would like to stop the recording. And I would like to stop here and